We are going to take the derivative of the logarithmic function, which is on page 324, and we're looking at theorem 3.15, which says that the derivative of, if you have a y equals to, let's say y equals to the natural log of x, ln x, then dy by dx has a simple formula. It's just 1 over x. Now is that simple or what? Okay. Now, so then let's see how that's proved. To prove it, there are actually two different ways to prove this, and we're going to do both because both are very short and sweet. So, for the first proof says that if y equals ln x, what does that mean? It means that e to the power y equal to x. That's the definition of the natural log. Okay, e to the power y is equal to x. Now, having said that, then we'll differentiate both sides of this equation. So then, to take the derivative of both sides, the derivative of e is e, right? So e, we'll write down this, and then derivative of y with respect to x multiplied dy by dx. This is the chain rule. And then the derivative of x is just 1. All right. So then, well, what does that mean? So then dy by dx equals to 1 over e to the power y. Okay. And what is e to the power y? It's just x. It's 1 over x. Proof done. Now, isn't that neat? A very simple proof. And because it's so simple, we're going to do something else. We're going to follow the inverse functions theorem. Now, to remember what is the inverse function theorem is that the inverse function theorem states this. Okay, that is dy. If f and g are inverses of each other, then the dy by dx equals to the inverse function formula is 1 over f prime of g of x, where g of x equals to y. So knowing this, then we can, and in this formula, f of x is, what happened to my stuff? Oh, right here. Okay, in this formula, g of x equals to the ln of x, okay? And f of x equals to the inverse, which is e of x. Okay, these two are inverses. So the inverse function theorem states this. So we're going to follow the inverse function theorem, which means the dy by dx equals to f prime. Okay, what is f prime? F prime is e of x of f prime of g of x. So f prime is e, right? And e of g of x, which is ln of x. And then 1 over, and e of ln of x is x, because, well, that's the definition. All right, it comes from this, e of y equal to x. So that's the second proof. So we have done two proofs of this, that the derivative of the natural log is 1 over x, which is short and sweet, right? Now let's look at the graph of the two functions briefly. I'm going to draw it out. So let's look at the graph in your book, which says that the ln x, which, as you can remember, is a slowly increasing thing, right? It increases very slowly. And then the derivative is just 1 over x, which means it's decreasing, but it always stays positive. 1 over x, for x bigger than 0, is always going to be positive. It just gets smaller and smaller. So this, and that sort of makes sense. Okay, and I should mention that there are some conditions. Okay, now x has to be bigger than 0. The condition here is x bigger than 0. Well, that's a basic condition because natural log is not defined for any negative numbers. We only care about the positive ones. So so that's just a quick simple condition. So having said all that, now that we see this simple formula and memorize it, let's use it on something. Example 3.77. Turn to the next page, which is on page 326. So let's try out example what did I say? 3.77, which says that we have some function f of x equals to natural log anyway, f of x equals to natural log of some polynomial 3x minus 4. All right, so what is the derivative? Well, we'll just apply this thing, then apply the chain rule, right? Because it's ln of more than just x, there's a pile of stuff in there, and whenever there's stuff inside, we use the chain rule. So to do the f prime, you write down, well, first, the derivative of ln, the natural log, is 1 over the stuff. Okay, here's your stuff down there. And if the stuff is more than just x, then we need to take the derivative of what the stuff is. What is the stuff? Okay, let's write it down. Plus 3x minus 4. Take the derivative of the inside, which is 3x squared. Use parentheses, plus 3. And that should be the answer. And it is. So that is the solution of this thing. All right, 3x plus 3, yeah, that's the answer. Now let's look at the next problem. The next problem says that the following problem on the same page, 3.78, we'll take the derivative again, which is f of x equals to the natural log of x squared sine x 2x plus 1. So we again will apply this principle, right? But applying this principle, but not forgetting that there's a pile of stuff in there. It's not just the natural log of x, a natural log of some complications, some function of x. So again, we will apply the chain rule. Now first, to calculate f prime of x, it equals to 1 over this pile of stuff, right? All of this stuff, and then once we write that down, we need to take the derivative of what's inside. So let's write down the pile of stuff here, which is x squared sine x over 2x plus 1. So far we have applied the derivative of the natural log is 1 over x. All right, but now we have more than just x here, so we need to take the derivative of this stuff, which is actually a fraction. And that's going to take quite a bit. But we'll apply the product rule. And, okay, so what is the derivative of this thing? I will write it over here, so that, because I'm kind of out of space. Therefore, I'll write it right here. Okay, the derivative of this thing, sine of x over 2x plus 1, equals to derivative. Okay, what's the derivative? That equals to, following the quotient rule, okay, denominator squared, 2x plus 1 squared. The quotient rule says take the bottom times derivative of the top. So the bottom is this thing times derivative of the top is a product, so we have to apply the product rule. The product rule of this thing says that is the first term times derivative of the second, which is cosine, plus second term sine x times derivative of the first term, which is just 2. I'll write down the 2 here. 2. All right. And yeah, so that is the top. And then continuing the product rule. And then the product rule continues says is bottom times derivative of the top minus the top times derivative of the bottom. So x squared sine x times derivative of the bottom, which is just 2. And I will write down the 2 right here. All right, so there's that. And now we have a big, now f prime of x means you have to flip this thing over, right? And maybe clean it up a little. And I will skip the cleaning up part and let you do that. But that should be correct. However, that is now that is not what the book did. So now you notice that the book didn't do this, okay? The book did simplify this thing first into a bunch of additions. So let's do that so that we don't end up with having to do a bunch of grunt work. It's a slightly less grunt work. In fact, we're going to mention this particular skill later, a similar skill. That is, because it's natural log, you want to when you're doing the log of multiplication, you want to reduce it into addition and subtraction, because that often makes things easier. So let's redo example 7.38. The same problem right here, and then use the properties of log. So f of x equals to natural log of each item. Okay, we'll break it down into addition and subtraction. Now x squared, and then plus natural log of sine of x, and then minus natural log of 2x plus 1. Now that makes life so much better, actually, because, well, addition is generally speaking easier to manage than, say, than this pile of stuff. Then we don't have to do the product rule or the quotient rule, sort of get around it. And you can't do that all the time, but with logs and exponents, you can often pull this kind of trick and make things easier. So let's take the derivative of this. Remember, the derivative of natural log is the derivative of natural log is 1 over x, right? So the derivative of this thing is we'll write the 2 in front by property of log, 2 over x, all right, plus natural log, this log of sine of x, and equals the, all right, the log of sine of x is, of course, is 1 over sine of x. Okay, first you write down is 1 over the object, and then take the derivative of the sine of x by the chain rule, which is cosine of x, and then minus 1 over 2x plus 1, derivative of that, f prime of x. I should write down this is f prime. All right, so then this is 1 over, and then take the derivative of what's inside the chain rule, and that would be 2 times 2. So that looks much better, right, than this stuff, and we're supposed to flip it over. And there will be a lot of fractions to deal with, but now we can skip all that and get to the point. So the answer is 2 over x, and cosine over sine is called the cotangent, so we'll write that down. Is the cotangent of x, and then over 2 over 2x plus 1. See, that is so much nicer, isn't it? Yeah. All right, so that would be the quick answer to example 3.78. Now, are those two answers the same? Let's hope so. I'm not about to go work on that thing to check it. So let's just move on. All right. And next, let's look at theorem 3.16. So let me clean off the board. Next, let's look at page 326, where we look at the derivative of the general log, that is not just the natural log, but any log with any base, and also the derivative of something of b to the power x, not just e to the power x, but any base. So the derivative of a function such as y equals to log bx, b is whatever value, right? B has to be bigger than 0, by the way. The requirement is b has to be bigger than 0, and b cannot be 1, because it doesn't, equals to 1 means has no meaning. I mean, it has no significance. So we'll restrict b only positive. With logs, we only care about positive values. And with that condition aside, then the derivative of y with respect to x of this function is 1 over x times the value natural log of b. It has to be a natural log, even though you're taking the derivative of any old base. So the natural log is going to adjust the value and make it come out right? So that's that's the answer. And then okay, we'll do this one first, and then do the next thing. So first, let's do how do you prove this one? Then the way you prove it is that if y equals the log bx, there's a formula in logarithm that says that y equals to okay. There's a formula in logarithm that says if log b any base x is the same as log x over log b. That, or ln. Maybe I should have said ln. Well, okay, I'll write down ln. This log is any base, okay? So we'll write down ln. That's the conversion. That's how you calculate log of some random base. Is you calculate the x divided by a known log, and then sometimes base 10, sometimes natural log, divided by a fixed value. And knowing that, then therefore dy by dx is we already know the derivative of ln is 1 over x. So this would be 1 over x times natural log of b, which is a base value. So it goes quite straightforward. And then the next theorem, the other theorem we need to prove is what happens, how to take the derivative of y equals b to the power x. Now, how would you take the derivative of that? We already know the derivative of e to the x is equal to itself. Okay, the derivative of e is e itself. Now, what about if it's b that isn't e? The translation, the adjustment is only slightly different. And the proof says this. We will use the implicit function. Okay, give me a second. Now, to prove this value, to find the derivative of this value, we will use a small trick. We'll take the natural log of both sides. Natural log of y is x times natural log of b. All right, so far so good. And then we'll do the implicit differentiation. Let's take the derivative of both sides with respect to x. Then we get derivative natural log of y is 1 over y dy by dx, okay? Because we're taking the derivative with respect to x. And then derivative of this side is just ln b, because we're taking the derivative with respect to x. And then now that you get this, then the solution is simply dy by dx equals to y times natural log of b. That's some number, okay? Because b is a constant. Which is, what's y again? Y is bx. So then b to the power x times natural log of b is the derivative of b to the power x prime. Okay, so that will be the formula. So you have two formulas for things that has any old base, like the log random base of x, follow this formula. And random base to the raised to the power x, if you need to take the derivative, follows this formula, which is similar to this one. The only difference is this one only has to multiply by 1, so you don't see the multiplication factor. With this one, you have to add the factor here. It has to take the natural log of your base. And that's the only, otherwise the derivative of b is almost b itself, except for this part. I mean the derivative of b to the power x. Okay, now having said that, then let's do an example. Example 3.79. That's yeah, there is no getting out of that one, which is fine. We will do example 3.79. Over here, we're at a similar page number. Maybe the next page, 327 maybe. And then where we have to do h of x equals to 3 to the power x, and then 3 to the power x plus 2. Okay, so how do you take the derivative? H. Take the derivative following the plan. All the plans that we've got. So h prime of x equals to, okay, we'll follow this rule right here, where the derivative of a number raised to the power x, okay, equals to the thing itself multiplied by a constant. That's the natural log of that number, in this case 3. Now having said that, let's do this. Now this thing is a quotient, so we have to do the quotient rule, which says you have denominator squared, and then you take the denominator, write it down. The quotient rule requires quite a bit of patience, but if you just do it like you're supposed to, and everything should work out. Denominator times the derivative of the numerator, which is the thing itself, plus times the natural log of the number. Okay, this is bottom times the derivative of the top, and then minus the top times the derivative of the bottom. This one, this bottom, not that bottom. The derivative of the bottom is again 3, the item itself, times the natural log of the number, if the number is not e. Alright, that's basically it. Now from this point on, we'll have to do algebra cleanup and stuff. Alright, so the denominator is probably not going to change. So we'll write that down, 3x plus 2 squared. And then the numerator, you have 3x times 3x, 3 to the power x, natural log of 3. And then you got subtracted it out over here. So all you have is this part, which is 2 times 3 to the power x, and then times natural log of 3. Yeah, good enough. That's how your book has it too. So we'll stop right there. Now remember, the 2 cannot be multiplied into the 3 because 3 is being raised to the power x. That's part of the function. So there's no way you can multiply it or anything. And then, yeah, that's good enough for anyone, right? And next you're gonna find the slope of the tangent line at some point. As always, please do that as a homework. As always, you take the derivative, you evaluate it at the given point, and then you use the point slope formula to come up with the equation of the tangent line. Actually, they don't even ask you to calculate the tangent line. They just want to know the slope, so you don't have to use a point slope formula. Okay, so let's move forward to the next part, page 328, which and we'll look at example 3.81. Next, let's look at page 328, example 3.81. Now here's a very interesting example. Take a look at this. Y equals to 2x to the power 4 plus 1, all raised to the power tangent x. Now that is something that we have not done before. Okay, we have done similar things. The first thing we have done is of course something like x to the power 3. Now how would you take that? You apply the power rule. Another thing we have done is 3 to the power, oops, I shouldn't write it so close to it. Another thing we can do so far we have done is 3 to the power x. Take the derivative of that. You use some kind of a log, right? We have, yeah. But, well, no, you don't use a log, but there's a formula for it that we just covered. But the point is this does not apply, okay? Because there's an x on top, so we cannot use this formula. And there's an x on the bottom, so we cannot use that formula. So we are stuck. Now, what do we do? Well, there's a trick to this. So to take the derivative of anything in this manner, you apply the trick. And the trick is you take the natural log of both sides, and then you use implicit differentiation. So now let's apply the trick. Take the natural log of both sides. Now, being that this is an equation, taking the natural log of both sides does not change the truth of the equation. Okay, so then so we'll take the natural log, which drops down the exponent, natural log of 2 to the power 2x fourth plus 1. See, that doesn't change anything. Okay, so we took the natural log, and then we take the derivative of both sides with respect to x. And then so the natural log of y, the derivative of the natural log is 1 over y dy by dx. And this side is just x, and then we will we will do the product rule, okay, which is not going to be that short, but there's no, so we'll take the first term times derivative of the second, which is this thing, 2x to the power fourth. The derivative of the second, let's draw some parentheses here. First term, and then we still have to take the derivative of the bottom of what's in here by the chain rule. So that's 8x. 2 times 4 is 8 times. Okay, so first term times derivative of the second, 3. Better not forget that. Okay, that's should be pretty good. Plus the second term times derivative of the first. The derivative of the tangent is secant squared. And then we'll write down the first, this thing, 2x4 plus 1. All right. So far, so good. And then we will. Now there's a y here, and y equals this whole thing. We got to put that in too. So then dy by dx equals to, we'll put the y here. Okay, y is 2 parentheses 2x plus 1 raised to the power tangent x multiplied by all this stuff. Now let's see, can we, the next job we will have is, actually there isn't much next job. Let's just leave it at that, okay? And I think that's all the book did, because the thing is there's probably not much cleaning to be done. So we'll call that, just, you write down this part, that's y, and then write down every single thing here into the parentheses. Stuff all that in here, and then that's the answer. So we'll skip the writing out part. Now next, example 3.82. I will clean off the board. Next, let's look at example 3.82, which is on page 329. Now by now you might think, oh boy, all the derivatives are getting longer and longer and more painful around here. Actually, this is taking a turn for the simpler life. Now look at the problem, okay? We're supposed to take the derivative of y equals to x square root 2x plus 1 over e to the power x sine 3 power of x. And you might think, that doesn't look that simple to me. You know, there's another quotient we'll be doing, and product, we'll be doing product rule, and it's going to be a headache. That would be true normally, but this example specifically show you how to get around that. It just happens that for this type of problem, multiplying and stuff, there's a neat trick that can make the derivative, taking the derivative a lot shorter and faster. And the neat trick is called taking the natural log of both sides. So let's do that. We'll take the natural log of both sides, and that equals to the natural log of products and quotients. The natural log of multiplication and division translated into addition and subtraction. Okay, so this translates into natural log of x plus 1/2 natural log of 2x plus 1, because this is the square root is the same as the power 1/2, which I put it in front. And then minus the stuff down here, which is the natural log of e of x, which is just x. And then plus natural log of 3 natural log sine of x, because sine 3x is sine raised to the power 3 times. So one of the logarithm rules is that you can take the power and put it in front, which is what I did here as well. The power can go in front of any log. So we have that. And then now we're going to do implicit differentiation. Take the derivative of both sides of the equation with respect to x. So that becomes 1 over y by the chain rule, dy by dx, because we're doing the derivative with respect to x. Natural log of x becomes 1 over x plus 1/2 natural log of that stuff is 1 over 2x plus 1, and then multiplied by 2 on top. And minus x, and minus, we're taking the derivative. Minus 1, the derivative of x is 1, minus 1, and then minus 3. The natural log of sine is 1 over sine x times cosine x. Okay, I am applying the chain rule. See? The derivative of natural log of something is 1 over that thing, then the derivative of the thing itself. If the thing isn't x, then you have to crank it one more level. So that should be good. And at this point, then the derivative then equals to, there's still the y here, and remember y is this thing, and we need to multiply y by all the stuff. So dy by dx equals to y. Okay, here's y, which we'll copy it. X square root of 2x plus 1 over e to the x sine 3 of x. That's a 3 of x. And then multiply by all the stuff, which is, okay, the first thing is 1 over x. The second thing is the 2 cancels out, so it's 1 over 2x plus 1. And then there's the value of minus 1. And then minus 3 of cosine over sine is called cotangent. Cotangent x. And that is the right answer, which is fairly easy, especially compared to what we would have been stuck with, like we did a little earlier with the product rule and the quotient rule and all that stuff. We're taking advantage of the fact that the natural log of a bunch of products and quotients translated into addition and subtraction, which is somewhat easier to do. It's still not extremely perfect, but good enough. That's the best we can do for now. All right, so let's then look at the next example. Example 3.83 actually is not so much an example as a proof. That is, we're going to find the derivative of y equal to x to the power r when r is any kind of number. Now y equals to x to the power r, where r is any real number. Now so far we have done is for the power rule, we have done x to the power n. That's the first one. And then later we also proved the power rule for x equal to m over n, some fraction. So far we have this. Now we'll have the power rule. It will extend it to apply to all real numbers, so that you know that the power rule works for everything. All right, now to do that, how are we going to do that? Well, we will use the natural log at this point to prove it. All right, now to prove that, okay, we'll continue writing here. So first we'll take the natural log of y equals to the natural log of x to the power r. And then we'll beat around it and hope that the derivative comes out looking peachy. All right, so then the derivative of this is 1 over y. We're taking the derivative with respect to x. Remember, r is just some number, okay, any number, like pi or something. But anyway, so 1 over derivative natural log of y is 1 over y dy by dx equals to, being that that's just a number, by the rules of log, we can write the number in front, okay? And the natural log of x is 1 over x. Okay, so far so good. And then therefore dy by, we'll write it over here. Therefore dy by dx equals to y times the number r over x, which is, what was y again? Y is x to the power r, which is x to the power r divided by x. Okay, so I have substituted the x to the power r for y. And what is that? That is simply r times x to the power r minus 1. And that is the proof of where the derivative of x to the power r is r x r minus 1, just like the power rule, and that applies to all real numbers. So, and that's that. Is that the end of the chapter? And that is the end of the chapter. So for now that is a neat trick for any time. Well, the point is, yeah, we're done. Let's look at the next thing. So let's look at some homework. For homework, we need to do, let's see. I would like you to do the examples I mentioned, as well as, which I will type below this video. Is on page 331, number 333, 35, 37, 39, 41, 43, 45. 345, I'm going to show you how to do it after at the end of this video. 347, 349, 351, 353, and 355. Now for 355, it mentions that the line that's normal to the tangent. And remember what normal means. In math, normal just means perpendicular. And how do you calculate the normal? You calculate the slope of the tangent line, and then you calculate the normal, because the normal slope times the tangent slope has to equal to 1. So normal slope equals to 1 over tangent slope. All right, so please go do your homework, and when you're done, come back and if you wish, look at me do numbers 345. So problem 345 on page 331 is it's just sort of a generic problem, but I thought I would do it just for the as a demonstration for the homework. So let's write down the problem. F of x equals to 2 to the power x. And as always, if you did this problem and didn't have any trouble, you don't need to watch me do this. There is no special trick to this. And then you can just move on to the next section. So anyway, we have 2 to the power x times log of base 3 7 to the power x squared minus 4. So there is just some details. Okay, there's always the details, but the idea is the same. The principle here is that here's one principle is if a function y is equal to log b of x, then the derivative dy by dx is equal, this is one of our theorems, is equal to 1 over x, right, times the number natural log of b. That's the first formula we're going to follow. And then the second formula is that if y equals to some number b to the power x, then dy by dx is equal to b to the power x, and then multiplied by a natural log of b. So those are the two principles two theorems we're gonna apply to do this homework. And once you realize that, then it goes pretty straightforward. And the next step is just trying not to mess up the algebra part of the story. So let's give it a try. F prime of x, therefore, equals to this is a product, so we'll take the first term times derivative of the second. So the first term is 2 to the power x, so far so good. The derivative of the second, following this rule, is equal to 1 over, well, we won't even write down the 1. Log of this thing is that thing itself on the bottom, is 7x squared minus 4, okay, which is okay. And then times the derivative of this. Well, you also need the natural log of the base, right? Because the base is 3. All right, so we need to multiply it by natural log of 3. And then we need to take the derivative of this thing. The derivative of this thing, according to this rule, is just b to the power x, is the thing itself. Okay, so we'll write down 7x squared minus 4. The thing itself times the natural log of the base, the number here, which is 7, and then you still have to apply the chain rule on this thing up here, which is times 2x. All right, does that look right? So you have to take the derivative, that's the bottom, and write down, and then wait a second. Did I write down too much stuff? Okay, it's right. The derivative of b to the power this thing is that thing itself, and then you have to take the derivative of what's on top. Plus, you have to remember the natural log of the 7. All those things. So if we keep all that straight, and then and that is just the first part of the product rule. So we did the derivative of the first term times derivative of the second. Then the next one, we're going to take the derivative, write down the second term, okay, which is this whole thing here, log base 3, 7 to the power x squared minus 4. Okay, that whole thing times derivative of the first. The derivative 2 to the power x, according to this rule, is 2 to the power x, and then natural log of 2. Okay, following this. And now that one is fairly simple, straightforward. And so now we got this pile of stuff here. All right. And so what do we have? Well, luckily, we can cancel out some of this stuff to make it slightly simpler. So let's cancel out this thing. So far, so good. And that's about all we're going to be canceling out. So so we're going to rewrite this whole deal. Okay. So the answer is 2x, 2 to the power x, and then natural log of 7 divided by natural log of 3. Now remember, the 2 here doesn't multiply into here because this 2 is being raised to the power x and you can't plug it out, basically. Well, whatever. Let's just keep, in other words, let's just keep it this way, okay? So that's the first part. Plus the second part, I don't even think you can do anything to the second part. Yeah, the second part, you just write it out. So you copy it again, log 3, 7. Actually, that you can add it up as x plus 1, but let's not do that because I didn't do that and I assume this is correct. Anyway, so x squared minus 4 and then times 2 to the x and then natural log of 2, and this is the correct answer because I checked it, I think. So that marks the end of this section and also the end of this whole chapter. So next chapter we're going to do applications of derivatives, which will be very exciting.